This is an example of a common emitter transistor circuit. And we see that the voltage, the source voltage is 15 volts. Beta, the current gain is 90. R1 is 5.6 kiloohms. R2 is 34.4 kiloohms. The collector resistor is 10 kiloohms, and the emitter resistor is 4.1 kiloohms. There's a 5 kilohertz input signal that's an AC that has an AC voltage amplitude of 2 volts peak to peak. And so 2 volts peak to peak is actually 1 volt amplitude. So it has a 1 volt amplitude. 2 volts peak to peak means from the, I'll show you in just once we get there. But what we want to do is we want to label the emitter, the collector, and the base of the transistor. We want to look at what kind of transistor are we using. We want to label where the output voltage is measured. Then we'll create a graph and we'll draw the load line, and then we'll figure out what the base current is. After that, we will calculate the voltages and the currents, and we'll add the characteristic curves. We'll look at the voltage gain, and then we'll look at the input and output AC signals to see how this transistor circuit handles an AC signal. So let's switch over to OneNote, and let's see if we go here to our PNP amplifier. So we've got our circuit. So the first thing we want to do is we're going to label the collector, the emitter, and the base. So we've got, this is our emitter. This is the collector. We'll just do C, and then this is our base right there. We'll just leave that just to give ourselves a little more room. Say this is the emitter, and I'm going to get rid of this line. The next thing it says what kind of transistor is in the circuit. Well, I'm sure we know that because the arrow points in right here, that this is a PNP transistor. And on the circuit, label where the output voltage is measured. And so the output voltage is measured when we have both a resistor, or emitter resistor, and a collector resistor. Then the output voltage is actually going to be on the collector. So right here, so this is going to be our V out on the collector. Next says create a graph for the characteristic curve of the PNP circuit. And so we need to calculate the values to draw the load line. So that's the first thing we're going to do is draw the load line. So let's draw our graph. And so our graph we know is this is our VCE. Or let's say VEC for now because we have a PNP, so we know we're going from our emitter to our collector. And our y-axis is going to be IC, and we're going to say our units are milliamps in this case and volts here. And in order to calculate the load line, we need to look at from the emitter to the collector the two cases of cutoff and saturation. So cutoff tells us our value, our maximum value for VEC. And so here we've got our V source, we've got our RE, this is E, and then we've got our C and our RC. And so if we look at the circuit at the point E at our emitter, because there's an open, so there's nothing collecting the emitter to the collector, then I know our E has to be at the same voltage as our source voltage. So I know that this is going to be at 15 volts right here. And because there's no current flowing, our collector is also going to have to be at the same voltage as ground. So this is going to be 0 volts. So then when we calculate the difference, remember that VEC, so VEC is equal to VE minus VC. So in this case, VE is 15 minus 0 gives us 15. So we're going to have 15 volts. That's going to be our maximum VEC that we can have. So VEC just means the voltage difference between the emitter and the collector. And now to calculate the maximum current we can have, we're going to use the saturation condition. And what that is we now have the same thing, our RE This is our E, this is our C, this is our collector resistor, and now we have a wire between E and C. And so if we have a wire between E and C, then the max current that we can have, IC, is going to be Vs over Re plus Rc, and that's going to equal, so IC is going to equal 15 volts divided by Re is 4.1 kiloohms plus our RC is 10 kiloohms. So if I just go over to MATLAB, I'm going to say that my Vs is equal to 15, and my Re equals, I think it was 4.1. So let's see, I'm going to say this is 4100. And my RC equals 10,000. Okay, and so now my IC equals Vs divided by, divided by Re plus Rc. Okay, so I get 0.011. Just go back, 0.011. So my IC here is equal to 0.011 amps or 11 milliamps. So up here, let's make this a little higher and say this is 11 milliamps. And so I'm just going to draw this line here, right? And that's the load line. So those provide the limits of where my circuit can operate, and it depends on my Re, emitter resistor and collector resistor together. They provide the limits for where my circuit can operate. Okay, so next we have to calculate the voltages. So in order to calculate the voltages, we're going to start with VB. So let's calculate VB, and we're going to use the voltage divider here to calculate our VB. So let's just draw a line, and we're going to say our VB is equal to our voltage divider, so it's going to be Vs times R2 over R1 plus R2. And so plugging in, that's going to be 15 volts times R2 is 34.4 kiloohms divided by 5.6 kiloohms. That's my R1 plus 34.4 kiloohms. And so I can go back again to MATLAB and I'm using MATLAB just like kind of like a calculator. So I'm going to, I already have my Vs, and now I'm going to have my R1 equals 5.6, so 5,600. And my R2 equals 3,400, 34,000, 34,400. Now if I want to calculate the, here if I want to calculate my VB, I can say that's equal to Vs times R2 divided by R1 plus R2. This is a little easier when I'm typing versus when I'm using the tablet, but I get 12.9 volts. So if I go back, Here I get VB is equal to 12.9 volts. So I can type that in, 12.9. And now looking at my circuit again, if at VB here I'm at 12.9 volts, then VE has got to be 12.9 plus 0.6. So I've got VE is equal to VB plus 0.6 volts. Because remember, my VE is going to be at a higher voltage than my B because of the following the arrow of the current. So my VE is going to be 0.6 volts higher. And so that means that my value is going to be 13.5 volts for VE. And the next thing I can do, I can't calculate VC yet, but I can calculate my IE. So the way I can calculate my IE is I'm looking at the voltage drop from across RE. So that's, I need the voltage drop, and so that voltage drop is going to be VS minus VE. So to calculate IE, I need to calculate VS minus VE over RE. And so that's going to be 15 volts minus 13.5 volts all over RE is 4.1 or 4.1 K. And so again, I can go back to MATLAB and so I can say IE is equal to let's see, VS minus VE. So I haven't actually calculated VE yet. So let's say VE is equal to VB plus 0.6. And there's 13.5. So then I can say IE is equal to VS minus VE divided by RE. And I get 3.65, so 3.66 times 10 to the minus 4. So IE is equal to 3.66 times 10 to the minus 4 amps. And that's equal to 0.37. I'm rounding one of those sixes, milliamps. So 0.37. And I'm going to say all of these are in milliamps. Okay, and this is IE, just to be clear. Okay, and so we can calculate IB from the fact that IE is equal to IB plus IC. And we know that IC is equal to beta times IB. So we can substitute that in for our equation for IE. So this is IB plus beta IB. We can factor out the IB and rewrite this as IB times 1 plus beta. So solving for IB, we get that's equal to IE divided by 1 plus beta. And in our case, then we're going to say IE is 0.366 milliamps over, and beta is, I think it is 90? Yeah, 90. So this is going to be divided by 91. Okay, so let's go back to MATLAB here, and MATLAB we have IE. Oops. So I know IB is going to equal IE divided by C1. Did I plug in beta yet? Let's see, we'll see. I kind of think I did not. Yeah, not yet. Okay, so so we're gonna call beta is equal to 90. Okay, and now I think I can up arrow maybe. Well, if I was typing, I could, we'll do it anyway. IB is equal to IE divided by beta plus 1. So 4.4, around 4 times 10 to the minus 6. So I go here. So IB is equal to 4 times 10 to the minus 6 amps, or 4 microamps. And that's equal to 0.004 milliamps. So 0.004 milliamps. And now I can calculate IC is equal to beta IB, and that's equal to 90 times 4 microamps. So let's go back to MATLAB again. And we've got IC equals IB times beta. What doesn't it like? Let's see. Oh, we're good, I think. Right, we're good. Okay, so we've got IC is 3.6 times 10 to the minus 4. 3.6. amps, which is equal to 0.36 milliamps. And just for a quick check, we can see that IC is just a little bit less than IE, so that makes sense. Okay, so now what do we do? Well, if we go back and look at our circuit, if we know IC, we know the current that goes through RC, then we know that if we multiply IC times RC, that's the voltage drop that we have at right before RC. So that's our VC. So VC has to equal IC times RC. So let's see, VC is equal to IC times RC. And so that's equal to 0.36 milliamps times RC is 10K. And so we're going to end up with VC is equal to 3.6. So we don't even need, right? We're going to have 3.6 volts. And so VCE is going to be 13.6 minus 3.6. So we're going to get 9.9 for our VCE. So right here, if we go back, and so we need to add our characteristic curves and where on the load line are we operating. So what we're going to do is we're using the VCE and we're using IC. So these two numbers are the numbers that tell us where we're actually operating on our load line. So the limits that we found earlier are the extremes, and that's not actually where we're operating when we are using an amplifier, when we're designing an amplifier. So we're at 9.9, so that's kind of be like here, 9.9, and our IC is 0.36, so we've got like 11, so we're like here. So we're pretty low on our load line, 0.36 milliamps. So let's see if I erase this. Of course, it deletes all of it. So we're like down here, pretty low on here. And so we're not really operating very well. We're kind of like here. So this is our base, so our IB in this example is 0.004 milliamps, so 4 microamps. So we haven't done a great job in designing this circuit. We are within our values. If we look at our here, what is the voltage gain of this circuit? Well, we know this is we know we can calculate the gain here because we know that our A is equal to a negative RC over RE, right? So then A is equal to a negative 10K over 4.1K. And so if we want to look and see what that is in MATLAB, see if we can get some. So 10K divided by 4.1 is equal to 2.4. So 2.4 is our gain. So here this is going to be equal to a negative 2.4. And so if we want to think about our out, V out is going to be V in times our gain. And so we know that our input AC signal peak to peak is 2 volts. So our amplitude then is 1 volt. So 1 volt times A. And so that means our output signal is going to be a negative 2.4 volts. And based on our information we have, so we've got an input signal that's going to be like way, let's see, up at VB. If we look at VB, our VB is at 12.9. So our input signal is going to look like this, 12.9. It's going to go up to 13.9, so it's going to look like something like that. And then our output signal is going to be look like this. And so remember that this is going to be 13.9, that our amplitude from here to here, this is going to be 1 volt. And now here on our VC, so our VC value is 3.6 volts. So we've dropped our bias down to 3.6, and we're going to have our amplitude, our new amplitude is 2.4, so it's 2.4 times 1 volt. So this is going to be at 1.2 volts. So I'm going to have something that looks like this, right? So, and I've got a inverting, so the negative right here flips my signal. So here I started and it's positive, and now here I start and it goes negative. And this is going to be, let's see, 6 volts. So that's what the circuit's going to look like. Probably if I were going to redesign the circuit, so a lot of times I might ask you to redesign the circuit. What I would want you to do is I would want you to move your where you're operating closer to be in between. So right now we're operating around 9.9, and I would want you to move this VEC over to say half of 15, so around 7.5, and increase your IC so it's more around 5 and be operating like right around here. And you can do that by adjusting your value for R1 and R2 to have a lower value, and yet that'll give you a bigger voltage drop across RE, which will give you a bigger current across RC, and that'll raise up my V out just enough so that I'm closer to this center spot instead of being higher.